All right. Hello, everybody watching virtually. Hopefully you guys are doing well. Thinking about you from afar. Hopefully life is doing all right for you. Okay. Got some stuff to pass out here. Joshua, you're the only one in here so far. So I'm going to get the stuff for you. Okay. Well, I might do this at the end. First, got to get the lecture out of the way. I was hoping some more people would come in. So maybe I might actually do this, hoping that somebody might benefit by me not starting it to find your work. Let's try and have as much partitioning possible. How your other classes going?
They're going all right.
Okay.
I need to work harder in biology, but
Yeah, there's a lot to memorize, right?
yeah.
It's not like in this class where understanding your way through things can get you where you want to go. No, you have to memorize every detail. What are you guys learning in biology?
Right now we're on like cells. Right now we just did molecular structure of cells.
Molecular structure?
Yeah.
Like the phospholipid bilayer.
Yeah. Exactly.
What does a smooth endoplasmic reticulum do?
That's a good question. That's why I'm saying.
What does the rough endoplasmic reticulum do?
I'm pretty sure one of those has to do with transport of nutrients or proteins, right?
Yes, the rough ER is embedded with ribosomes. What do the ribosomes do?
Ribosomes create proteins.
Yes. So the rough endoplasmic reticulum is embedded with those ribosomes making the macromolecules. There's a smooth ER. What do you think that thing does? It was fruitful to wait. Look at how people are just coming in droves. The smooth endoplasmic reticulum is more of a lipid creator. And it's more of like a lipid factory. Right? Because it's smooth. It's more about creating the lipids needed for the cell. And then what else is there? Okay, so then there's this. Okay, I'll wait to undo this one here. This is Joshua, Travis, and Kinsey are here, so I can hand you guys your stuff. Okay, what does the Golgi apparatus do? You sack any quarterbacks this morning? Here you go.
No, I don't have it.
You don't have any. You don't have football in the mornings. The Golgi apparatus. You remember what that does? Is this the kind of stuff you guys are learning about right now?
Not exactly like well, right now we're learning about like what connects nucleotides and like the carboxyl groups and
Uh-huh.
how those are connected, and how
Uh-huh.
there's a lot of those.
Yeah. That's cool. It's cool how the hydrogen bonding occurs up and above and below the spirals. It's cool. Okay. Well, I'm gonna quiz you in the mornings about some biology, and you need to teach me or make me review a little bit. All right? Be like, did you know this fact? Okay. So, guys, did you get the email I sent you?
We got a notification.
Yeah. Yeah. Okay. So, I have to swing this by my colleagues, but we're moving at such a rapid pace that by the end of the semester, which winds down on the 24th of November, we'll be done with the material like a week in advance. So like the last 3 class periods, I may make just optional review. So show up if you need it, don't show up if you don't. Get some extra sleep and extra hours of studying for the final in here and your other finals. You know, if we can make that happen, I will. If not, if, my colleagues say, well, that's too many days off, maybe we need to add more material, then that's what I'm going to have to do. But right now, I think I'm going to try and push for giving you guys the last 3 class periods being optional and showing up if you need it and asking questions about the comprehensive final exam in here. The comprehensive final exam is worth 30% of your grade, whereas the midterms are worth 25. So it is more of a significant exam. Furthermore, the word comprehensive, and it implies that it will be all-encompassing. It will have questions that range from chapter 1 all the way to chapter 7. If that's where we stop. If we have to continue, then it will have stuff from chapter 8 as well. So we'll see. We'll see. I'm looking out for you guys. I want you guys to get extra sleep during finals and have some more of a chance to do well in not only this class, but your other classes. So today is a review day. I'm just going to ask who has any questions, and we're going to review for the test on Thursday over chapters 3 and 4. And then if there's no questions, I'm going to move on with chapter 5 and the material that will go on the third test. So we have test 1, test 2, test 3, and then the final. And Thanksgiving is the 26th of November, and we'll all be done by the 24th. The 24th is when we take our final in here, starting at 8, ending at 9:50. It doesn't have to be at 9:50. If you guys require more time, I'll give you more time. Yeah, I'm not like that. I'm not the kind of person who would want to punish you for wanting some extra time. However, I'm not going to stay here till 2 p.m. Maybe 10, maybe 10:30, the latest. I'll be willing to give you some more time to finish up. Okay. With regards to graded work, there's more graded work that needs to be turned back. I have even more stuff over here. I'm not sure if it's it's not separated per student. So I'd have to kind of sift through it and organize that. But I'm just going to sit here and I'm going to kind of get these papers in order and give you some time to think about any questions you have for review. And if you don't have any questions, I'm going to move on after I have sifted through all these and turned back your work.
May you please go over arc length? I've been having so much trouble with it.
Yes. How you doing, man?
Good. Hey, I've been having some email complications. Did you get my quiz?
I think so, yes.
Okay, thank God.
I think yes. Thank God. Yeah, I think I did get your quiz. If not, I believe I got it. You can always resend it. I'm not going to be like, you didn't send in your quiz, this and that. I'm a pretty chill guy, if you guys haven't noticed. What I really want for all of you is for you to be successful and for you to work hard. If you guys just work hard and keep asking good questions and keep participating, I'm as happy as can be. Of course, I want all of you guys to become mathematicians. I want to convert all of you to come to the dark side. But if you don't want to do that, then I understand. My feelings will only be hurt a little bit. I hope that even if you don't want to become a mathematician, that you attain a more of a thorough appreciation for mathematics after this class. And we are about to go over arc length, Anthony. I'm just sifting through these papers. I better write that down so I don't forget. One of the things we're going to go over is arc length. Guys, anything else?
The like tree graphs and models and like how to
Very good.
like, find the points. And,
Sure. Graphing, right?
Yeah.
Graphing and graph transformations.
Yeah.
Oh yeah, this is very important stuff for the exam that's going to be happening on Thursday, next class. So it was really good to review that stuff. Anything else? Anything else that's not synced in yet that you would like some more help with?
Simple harmonic motion, like you know how like, we get the graphs and all that.
Mm-hmm. Let's call it show. Call it show. All right. I'm done sifting through these. Josh is here. Travis is here. And Kenzie is here. I'll hand these back to you guys. Oh, wait a second. Have I entered this in? Have I entered this stuff in yet? I don't think I have. Oh my goodness. Okay, I'm gonna need you to hand that stuff back. 'Cause I don't think I've entered it in. I don't think I've entered these grades in. No, you don't have to get up. I'll come to you. That's my mistake. Yeah, I don't think I've entered this stuff in. So, yeah. Okay, I'm gonna have to hand it back to you on Thursday. I think so. Yeah. Yeah. If I'm missing something, we'll figure it out. I'm on path. I did this the other day in my other class, and that is what made me second guess myself. And now I'm glad that I second guessed myself.
You also go over 4.3, sketching and all that.
4.3.
Yeah.
As you wish. Okay. Let me just not mess things up. Because if I give it to you guys, who knows what you're going to do. You might lose them, and then we're in a predicament. I need to enter them before I give them back. Okay. Anthony, in terms of your graded work, here's two options. Well, actually, I can scan it and send it to you, or you can just look at your grade and look at your solutions.
Okay.
Look at the solutions that I will post.
I think I emailed you my homeworks, but they didn't send, so I'm going to send them again. I'm sending them right now.
Got you. Okay. No worries. And guys, if you still have homework that you haven't turned in for this upcoming test, feel free to turn it in on Thursday to get those points. Is this your work, Joshua? It doesn't have a name on it. It seems like it's yours because this is the same kind of paper.
Yeah, it's
Okay,
mine.
it's yours? Okay, all right. Now I know what's going on. Okay. All right. So let's begin to review. Let's start off with arc length. So in your book, arc length is S, which is equal to r theta. So this only works for circles, but this is only what you'll be given. You'll only be given circles. There's also something that kind of relates to circles that we didn't really talk about much, but we probably should. So here's arc length. It says, if you traverse some angle theta of a circle of a radius r, how much is this distance if we straighten it and measure it with a straight edge? So the other day, I graciously donated a hair tie. If I can find it here. Here it is. So take a look. You get a circle. All right. Let's say here's our circle. We're going to move through an angle right here. And then the arc length is you snip the circle, you straighten it out, and you measure how much is that. Because as it's curved, you can't measure it. I don't have a ruler here, but we all know rulers are like straight objects. How can I measure a circle if it just keeps changing, right? It's hard to accurately measure what that distance is with the straight edge. And that's the only way we know how to measure using straight measurements. So we invented the mathematics of knowing just how we can get a little piece of the circle, mathematically calculate what it would be if we straightened it out flat. That's what arc length really is. Arc length is really this distance S, and it's given to us by r times theta. So let's say, who here knows what the Large Hadron Collider is? The Large Hadron Collider. It is a particle accelerator that is found in Geneva, Switzerland. You guys never heard of it? It's really important. So how large is it? Let's see. It's 16.6 miles in diameter. It's a circle. 16.6 miles in diameter. Where they get protons, accelerate them to 99% the speed of light, and then smash them together. What happens is the protons break up into their elementary particles, and they study these elementary particles that way. Who here has heard of the Higgs boson? It was in the media called the God particle, but theoretical physicists hate that word used that way because it's has nothing to do with religion. The Higgs particle is just hypothesized and then verified particle that gives mass to all other particles in specific interparticular interactions. But anyways, the Large Hadron Collider is a circle of a diameter 16.6 miles. So then that means it has a radius of 8.3 miles, right? So what I want to know is if the protons, let's say P plus over here, started at here and they were rotated through pi over 3 radians. And do not forget, this angle has to be in radians. If you use degrees there, it's going to be wrong. Make sure to write that down. Put huge stars on it. Highlight it. Make sure that you understand that if I'm going to use S equals R theta, that the angles must be in radians. Okay? So let's say we got a proton. It rotated through pi over 3 radians. And now it's over here. How much distance did it cover? We can discover how much distance it covered by using S is equal to R theta, which is equal to 8.3 miles times this radian amount, pi over 3. So let's see how many miles of the proton moved during that trip that it took. It's not even all the way around the particle accelerator. We have 8.3 times pi over 3. That's around 8.69 miles. 8.69 miles, man. They get these protons and they move them 99% the speed of light. Do you guys know how fast the speed of light is? Have we gone over scientific notation here? We have? Okay. The speed of light is 3.0 times 10 to the 8 meters per second. What is that in miles per hour? This is actually a really good conversion of units practice problem that we can do. This is the speed of light. What is it in miles per hour? Because we think of speed, to me, if you don't tell me how it is in miles per hour, I don't have an intuition for it, right? We all drive cars. We all know kind of how fast 60 miles per hour is, 40 miles per hour, 20 miles per hour. So let's kind of think about how fast light moves in miles per hour. Because you for this test, you will have to convert units. Okay, so there will be a problem where you'll have to convert units. So this is a good little cool example we can do. Let's see what the speed of light is in miles per hour. So notice that this is 3.0 times 10 to the 8 meters over seconds times in 60 seconds. How many minutes do I have? 1 minute. And then in 1 minute, how many? Oh, in 60 minutes, how many hours do I have? 1. So once I cancel out these units here, now I have it in meters per hour, but I need it in miles per hour. So this ends up equaling something in meters per hour, whatever this number is. Let's find it. .08 times 10 to the 12. Now, guys, that 3.8 times 10 to the 8, it really means this. 1, 2, 3, 4, 5, 6, 7, 8. What is that? If this is a number here, that's 1 million, right? This is in the millionths place. This is in the 10 millionths place. This is in the 100 millionths place. It moves 300 million meters every second. Let's create an intuition in miles per hour because this is still in meters per hour. So in 1 mile, how many meters do we have? I don't know. I'll look it up. Let's see. (1,609 meters). There's 1,609 meters in 1 mile. So cancel out that. And now we're going to get it in miles per hour. So I just need to divide this by 1,609. Let's see here. Oh my goodness. The result, guys, is astonishing. This ends up working out to this many miles per hour. This is how fast light moves. 671,224 363. That is how fast light moves in miles per hour. 671,224,363 miles per hour. Imagine the speeding ticket a particle of light would get. Probably an infinite amount of dollars. Fine. Right? But a beam of light can travel across the Earth 7 times every second. All right. So actually, in the particle accelerator, they get protons and they accelerate them to 99% this. So basically, this, maybe a little short of this, you know. Maybe in the particle accelerator, they get the protons moving that much, maybe that many miles per hour. What they do is they use really strong magnetic fields, and magnetic fields can move charged particles. Why am I talking about this stuff? Well, I just kind of want to make it interesting. We converted a really cool unit to see how fast light moves. This stuff right here, this is how fast it moves. And then we calculated the arc length over here. So I believe we've effectively covered that. Notice that actually there's one more thing we could talk about. Let's say you're given that something is moving on a circle. You don't know what its radius is. R is equal to question mark. R is equal to question mark. But you know that it rotates through an angle of like pi/4. And actually you're given that S is equal to, 4 miles. Notice that S equals R theta would allow us to calculate what R is, for instance. So let's say you're given 2 pieces of information. You're given the arc length and the angle, but not the radius of the circle. But you knew that it was rotating through a circle, right? Well, then you may assert that if it is rotating through a circle, then S equals R theta applies. And if you keep theta in radians, please keep it in radians. You can algebraically solve for R, dividing both sides by theta. So I get S over theta is equal to R, which then this ends up equaling 4 divided by pi/4. When you multiply by reciprocals, you get 4 over pi over here. So this becomes 16 over pi, which this is approximately how many miles? 5.09 miles. And this is what your radius is. So you can actually calculate the radius of something, of a circle, if you know that whatever is being rotated through is being rotated through a circle. And now you may think, well, how is that? How is that important? Well, let's say you want to, calculate what is the diameter of a forest or whatever. And you rotate this many angles from this, landmark to this landmark is this much angle, and you go then and you walk around that forest and you see how many miles that took. You can then calculate what is that radius through the trees, because walking through the trees is very difficult, nearly impossible to be able to calculate what is the distance through the trees. But you don't have to go through the trees. You can actually just use mathematics to calculate what that radial distance would be. Now, your calculation becomes more and more accurate if you're really going around it in a circle. The more you deviate from a circular traversion, the more your radius becomes inaccurate. But yeah, this stuff is like practically useful. People have been using this stuff for a long time and they continue to use it every day. So this isn't just mumbo jumbo, guys. It's very practical. It can be used to discover things. So then we discovered S equals r theta. We can, given the r, given the theta, calculate the s. And then we were known that given the theta, given the s, we can calculate r. Just know that given an s and an r, you can calculate theta in a similar fashion. I can't give it all to you for free, right? It can't be all for free. I gotta give that, I'm gonna let that one stay in the air. Who knows, maybe that case might show up on a test or a quiz, who knows? Did you guys know light moves that fast? In the hundreds of millions of miles per hour? It's so hard to even have like a grasp of how fast that is. What's the fastest any of you guys have ever been? Oh, I guess in an airplane, right? If you go in an airplane. Or in a car, what's the top speed you ever gotten? I've gone 135 top speed on the highway.
I've only gone like 106.
106? That's so fast, but it's like nothing compared to light. That's 106. That's in the hundreds place. Light is in the hundreds of millions of miles per hour. That is astonishing. We live in such an incredible universe. Now it's time for graphing and graph transformations. Again, I'm going to resort to technology over here. If only Harrison was here. And actually Kinsey, they're the computer science people. Thank you for your work in computer science, because you allow me to just, cheat. I don't have to draw this stuff. I can actually have a nice graph over here. Let me hit share screen. Yep. Yeah, when I draw it, it usually never comes out right. There we go. All right, beautiful. Here we go. So I will draw out one thing, or two things. You guys know why cosine looks like this, right? At angle 0, it assumes its highest value. Then it just does this thing on forever. if this is some angle theta, this is a cosine of theta, and it dips down to the lowest value, -1. You know, where is it crossing the x-axis here? Is when cosine equals 0 for the first time in its life, and that's pi/2. Cosine then equals -1 where? For the first time in its life. That's right, pi. And then cosine then equals 0 for the second time in its life. And you get the picture, right? Over here, this is a 2 pi. So now that you know, you should know that cosine looks like that and why it looks like that. It's from a cosine of theta table. You pick various thetas like 0, pi/2, pi, and then you say, what's the cosine of 0? That's 1. I go to 0, 1, I put a dot. Cosine of pi/2. What is this? Oh, well, that's just 0. I go over here. I find 0. I put a dot. Oh, what is the cosine of pi? Oh, well, that's just a -1. I go to here. I find a -1. I put a dot. And then when you connect the dots, you get this curvy stuff. All right, same thing for sine, except sine assumes its lowest value initially. No, I said that wrong. Sine assumes the value 0 initially. Its lowest value is not 0. Its lowest value is -1, right? This is sine of theta. And then the most important thing to realize about graphs and how to graph them is this table. Create this table, put dots, connect the dots. And there's one more piece of information, and that is with regards to this general formula, where your y of theta, for either sine or cosine, it doesn't matter. I'll put sine over here. Can you see that, Anthony? It just says y of theta is equal to a sine of theta of, it's y of theta is equal to a sine of b theta minus c, close parenthesis, plus d. So can you see it? Yeah. Okay. So, what is this? Amplitude. How can we calculate the period?
Was it 2 pi over b?
Yes, very good, Travis. What is the horizontal shift, and in what direction, and why? It's not C all and so on. B over C, right? If it's greater than 0, it goes to the right. And if B over C is less than 0, it goes to the left. So that ratio tells you whether it's going left or right. And what is the amount at which it goes left or right, as you said, Travis, is C. But whether it goes left or right is dictated by B over C. But let's see over here, all right? Let's like play around with Desmos. You don't get Desmos on the test. So it's best to play with Desmos prior to the exam and attain an intuition. If you want to do good on the exam, know how to graph stuff like this, but also know how the graph transforms. So here's the transformation. Here's sine of x. Let's transform sine of x, okay? Let's increase the amplitude by 2. All right. Now, on top of increasing the amplitude by 2, why don't we now actually create a different period. Notice that red sign and green sign have period 2 pi over 1, which is 2 pi. But over here, they have period 2 pi over 2, which then compactifies it to having a period of just pi. So notice that this blue is going through 2 full cycles as opposed to the 1 cycle. The red, is this 5 pi over 2? Okay, I've gone too far here. Let's do here 2 pi over here. So red goes through a full cycle at 2 pi, and so does green. Actually, it goes through a full cycle at 2 pi. But if we notice when we modulate this parameter here by adding a 2 here, notice that this thing is going to go through a full cycle at pi, and then a whole nother full cycle at 2 pi. So we've effectively changed the period by putting that number 2 there. We've made it actually repeat itself twice as fast. So that's the B. I changed the A, I changed the B. What happens when I change a C? All right, now let's shift it by some thing with having to do with pi's here. Let's say pi over 4. Or let's say pi over 2. Even better. Notice, what does the green look like with respect to the blue? Notice that as Travis hypothesized, that the horizontal shift was by a value of pi over 2. Because if you notice that this crest and that crest, oh wait, am I comparing the right ones here? I need to compare this blue, right here, boom, with the green. They won't both simultaneously stay up. Oh, there we go. So notice the phase shift. How much is that phase shift between the blue and the green? Well, we know it gets phase shifted to the right because C over B in this instance, C is our pi over 2. And what is our B? 2. So this breaks down to pi over 2 times 2 over 1. Cancel it out. So we get pi, which is greater than 0. So it's going to shift to the right. But how much did it shift to the right? Well, if we measure from this peak to that peak, the difference between pi over 4 and pi over 2 is not necessarily pi over 2, is it? What is the difference between pi over 4 and pi over 2? Correct. So what's going on there? So it shows you that it's actually being shifted horizontally by B over C. No, I should just put that because that's confusing. It's already negative. Okay. So it wasn't necessarily true that it gets shifted over by C. You have to incorporate that C over B. And this is why. And that kind of makes sense now in hindsight, because you have to realize that the C does influence the B and the B does influence the C, because B influences how frequent are the oscillations occurring. And C just tells you shift by a certain amount. But you have to incorporate how frequently the oscillations are occurring. Okay. So take a look. B over C, in our case, Do I have C over B over here? No wonder. My dyslexic self has done it again. Should say B over C. That's what is it? Okay, so 2 over pi over 2, right? So then our B over C is 2 over 1 times 2 over pi. This becomes 4 over pi. What am I doing over here? No, I think I had it right the first time. Yeah, I think I had it right. It's C over B. Did I write B over C over there? It needs to be C over B. Right? Because the actual phase shift is by pi over 4. Our C is pi over 2. Our B is 2. So it is indeed C over B. It's the ratio C over B. C over B. Is that what I had? Or did I erase it and redraw the same thing?
You have B over C.
I have B over C. Yep, that's flipped the wrong way. Okay. It is indeed C over B. Okay, so notice that this ends up equaling pi over 4. And this ends up equaling how much we got phase shifted horizontally. Now, I know what you're thinking. Why doesn't this have a negative on it? Because it's negative pi over 2 over there. Why am I writing positive pi over 2 over here? Well, it's because that negative sign is in the standard format right here. If I were to have a positive pi over 2 over here, that is when I would actually put a negative over here. Because for the expression to have a positive value here, that means C was negative, and a negative times a negative is a positive, making this a plus. So just remember, if there's a plus here, that means it's negative pi over 2. If there's a minus here, that means it's just pi over 2 because of the standard form. And last but not least, let us incorporate a vertical shift. Boom. So that last number is very easy to predict. That plus D raises it up by D increments if D is positive, and plus D depresses it down by D increments if D is negative. But you get all of this stuff if you create a table like this. You get this plot if you create a table. So for instance, watch, I'll be able to reproduce, let's say, this point and this point. Notice that this point, 0, when I put input 0, I'm going to get a 3. When I input pi over 2, I'm going to get a 7. So here, let's do a y of theta graph. Let's pick 0 and pi over 2. Notice that y of 0 is equal to what we have up there, 2 sine of 2 multiplied by 0 minus pi over 2, everything plus 5. Notice that this ends up becoming 2 sine of just negative pi over 2 plus 5. I know sine is an odd function, more review. So that means this equals this. Right? We all know why that's the case. And I know sine of pi over 2 is 1. So this breaks down to negative 2 plus 5, which is positive 3. I go to 0. I go to 0. I find a 3, I put a dot. Then y, what is y of pi over 2? Pi over 2 is just 2 sine of 2 times pi over 2. Oh, and we got a minus of pi over 2. And don't forget to add a pi. So notice that this ends up equaling 2 sine of pi minus pi over 2 plus 5. Oh, but then this equals 2 sine of pi over 2 plus 5. What is sine of pi over 2? That's 1. So this becomes 2 times 1, which is just 2, plus 5, which equals a 7. Oh, I go to pi over 2, right here. I find a 7, I put a dot. So the table will allow you to get the graph, no matter what. But I will expect you to understand what does A, B, C, and D do to graphs transformations. All right. And yes, it's C over B, not B over C. Clearly, if you think it's C over B, and if you think it's B over C and you graphed it, you'd realize that that's not what's outputting appropriately. So, okay. So then that's graph transformations. Now there's simple harmonic oscillators. This is simple harmonic motion. Things that periodically repeat like that, that means we call that going through simple harmonic motion. And it's modeled by sine and cosine. Also, don't forget your other trig functions like tangent, cotangent, cosecant, secant. Know how to graph them and how to transform them. Okay? Simple harmonic oscillators. Let's go to that section here. See if we can find a nice problem. Remember when we did the deer problem? That was deer population problem. That was simple harmonic. So let's do like a spring problem. Let's do a mass on a spring. So let's say you have some mass on a spring and its position oscillates from some initial x naught. So here's your x-axis, here's your y-axis, and this is what it is at t equals 0. So x naught is equal to our function y of 0, where y of t, let's say it equals 2 sine of t. Okay? All right, so notice that if this is x naught at t equals 0, we got y of t is equal to sine of 0, which is equal to 0. So that means this position is what we're setting equal to 0 in the simple harmonic oscillator. That means this is position 0, and anything to the left is a negative position, and anything to the right is a positive position. Where is the mass at t equals 5 seconds? How do we find it? Let's say that y of t is in feet. How many feet to the right or to the left is this function? And actually, you want to know what? I'm not going to say t equals 5 seconds. I'm going to say t equals 5 pi seconds. I do this for teaching purposes, so that the function is easy to evaluate. How do we determine where is it at t equals 5 pi seconds? Well, what is that? Oh, yeah, that's right. We evaluate the function at t equals 5 pi. Y of 5 pi is equal to 2 sine of t, which is being replaced with 5 pi. So what is sine of 5 pi? Oh, I know. I don't know what sine of 5 pi is, but I know I can subtract any multiple of 2 pi from any angle and land back in the same spot, right? So I know that that equals pi. So this is the same thing as just sine of pi times 2. And what is the sine of pi? That's right, it's 0. So this is 2 times 0, which is 0. Ah, at t equals 5 pi seconds, it's right back where it started. Let's find a non-trivial position. Where is the mass at t equals pi over 4 seconds? To do so, what do we got to do? Evaluate the function at pi over 4. Please tell me this one. What is the sine of pi over 4? Thank you. So this becomes 2 times root 2 over 2. 2's cancel. So this becomes root 2 feet. And since it's positive, that means the mass is over here. At t equals pi over 4, the mass is over here to the right. by a distance of root 2 feet. How much is root 2 feet? Oh, get out of here, you. 1.41 feet. You guys seem, maybe a little bored or disinterested, but every mechanical device you have right now, that watch, your car, your phone, that watch, this computer, functions off of simple harmonic oscillators. Because if you think about it, what about like pistons and gears in a machine? If you know, how do you fit all that metal that works together to have a car work, right? Well, you know that, okay, if I know the simple harmonic position of, let's say, one of the pistons, I can ensure that no pistons will ever collide with each other, because I can create the whole machine in a way in which I know that this mass will be here and another piston can occupy this location at t equals pi over 4. And that at t equals, let's say, 5 pi, that the piston better be not in that location, because that's where the mass is going to be, so as to prevent collisions inside of your mechanical device. So this allows you to engineer stuff. It allows you to predict what your engineering will do. It allows you to make sure that the mechanical device that you're creating or inventing doesn't destroy itself. Now, of course, that's assuming everything is functioning properly. If something is going wrong, then maybe the masses might collide inside your mechanical device. And then you better go to AutoZone or O'Reilly's. I don't know which one's better. Maybe you guys can tell me. That's simple harmonic motion. What's 4.3? What is that about? Transformations. Okay, we already did transformations. If you guys don't have any more further questions, you are free to leave. I need to record these for you into the grade book, and then once I do that, I'll return them to you on Thursday, which is in 2 days, and that's when you'll be taking exam number 2. As promised, it'll be slightly more difficult than the first exam, because I did make that first test too easy. But I will include bonus points, okay? I'll include a lot of bonus points. And it's not going to be like ridiculously harder either. This is going to be a little harder, because that first test was a little too easy.
So much, Professor.
Yes, sir.
Hey, one thing. Okay, my email's like bugging out. I don't know why. I'm sending you like all my homework again. Just give it a second.
Okay. Sounds good. Thank you. All right, sounds good. You holding up okay? Talk to you later, Anthony. I hope you and your family are doing well. I'm keeping you in my thoughts and prayers.